So in today's lecture, we'll study about the material elaboration and nanofabrication techniques for spintronic devices. So in earlier lecture, we have seen the fabrication of magnetic nano. We have seen the fabrication of magnetic storage devices, and we have seen what are the different techniques of patterning image on any substrate, right? So those techniques, what we have seen with the lithography techniques, we have seen certain differences between their between their cost of equipment. They actually have seen the differences between their cost equipment and advantages and disadvantages, and the features, and also we have seen, right? And today's lecture we'll see the metal elaboration and nanofabrication technique for spintronic devices. So here the fabrication, when we speak about the fabrication, we need to first concentrate on the fabrication of nanomaterials, nano devices, right? Nanostructures, either by a PVD process or CVD process, right? So in that criteria, we need to understand what are the materials elaboration and nanofabrication for spintronic devices, right? So the material elaboration and nanofabrication techniques for spintronic devices are nothing but so these are some of the device making. So these are some of the device making where we need to understand what are the devices. So see, this is one device. So device making, right? So these are all the spintronic devices. Spintronic devices in the sense devices which work on the spin of the electron, right? Spin of the electron. So we have the electron has two properties on the charge and spin. So charge consumes electronics, whereas when started concentrating on the spin, then the spintronic devices came into existence. Right? So metal, why it is important? Why this type of elaboration and nanofabrication technique for spintronics is important? As a researcher, we need to understand and control. We need to understand and control the properties of materials. To develop new knowledge materials and working principles. So where we need to understand the theory and modeling of magnetism and spintronics. We need to state the art, materials and devices and access to challenging characterization methods. Right. So the theory and modeling for magnetism and spintronics, you need to state the state of the art of the materials and devices and access to challenging characterization methods. So as a researcher, we need to understand and control the properties of matter, right, to develop new knowledge materials and its working principles. Right. So why it is difficult? And why it is important? Earlier, why it is important, and now why it is difficult? Here we need to combine the material elaboration. We need to combine the material elaboration to nanofabrication. Fabrication, obviously, after the fabrication of the materials, we need to go for the characterization, and we need to show the various properties by characterizing, and then we need to understand the theory and the modeling for magnetism and spintronics. Right? So the theory and modeling also need to be done. Modeling also need to be done for magnetism and spintronics. Right? So, and then we need to understand, that means the material elaboration and nanofabrication and character techniques comes under the material science. So material sciences and the nanofabrication, it requires the technologies, and the characterization are nothing but the measurement techniques. That's why it is difficult to learn is, one is we need to understand the materials of the science of the material, and we need to fabricate the technology. What is the technology that is required to fabricate that particular material, right? And then we need to study certain measurement techniques. What are the measurement techniques, or what are the characterizations of various properties, right? So the laboratory nanostructure at magnetism. So these are the ferromagnetic materials, metals and different sputtering techniques, techniques of fabrication, right? So molecular beam epitaxy, metal and semiconductors, and molecular beam epitaxy and sputtering. So we have here nanoclusters, we have nanowires, right, and thin films, right? So these are the thin films, and these are the nanowires, and these are the nano clusters, and we have the nanofabrication. So fabrication is what between the approximately 100 nanometers, and the width is around 35 nanometers, right? So we need to go for different ferromagnetic materials like metals, semiconductors, and molecular beam epitaxy, and what are the different techniques where we can form where we can fabricate the materials, right? And we need to study about the structure, magnetic, optic, and electronic properties, right? So these are nothing but the thin films, nanowires, nanoclusters, and nanofabrications, right? So the basic outline is, first we need to understand how the material is growth, how the material is grown, and we need to go for nanofabrication and some meteorology tools. And fourth one is some examples of combination of top-down and bottom-up fabrication techniques. So we need to understand this type of examples also, right? So how the material is grown, what is the nanofabrication, and what are some meteorology tools, and some examples of combination of top-down and bottom-up fabrication techniques. So when we speak about the material elaboration, thin films and novel materials, which includes alloys and heterostructures. So thin films and novel materials, which includes alloys and heterostructures, right? Deposited by physical or chemical means. That is material evaporation or sputtering, chemical decomposition or electrolytic growth, right? So thin films and novel materials like alloys and heterostructures deposited by physical or chemical means. We have material evaporation or sputtering, chemical decomposition or electrolytic growth, and we have the material evaporation or sputtering, we have chemical decomposition or electric growth, and the techniques involved are the molecular beam epitaxy and sputtering deposition and ultra high vacuum evaporation chamber, and another technique is a pulse laser deposition, that is PLD technique, right? So these are the material evaporation or sputtering techniques. So these includes the molecular beam epitaxy, sputtering deposition, ultra high vacuum deposition, evaporation chamber, and we have pulse laser depositions, PLDs. Whereas in chemical decomposition and electrolytic growth, we need to study about the chemical vapor deposition, that is CVD. We need to study about the CVD, and other is atomic layer deposition, that is ALD, and other is electron beam induced deposition, that is EBID, and other is electroplating. So these are the chemical decomposition or electrolytic growth materials, right, which includes the CVD, ALD, electron beam induced deposition, EBID, and electroplating. So when we say in this material elaboration, the thin film growth is mains important role. So thin films on a flat substrate, 3 angstroms to 100 nanometers. So the materials like amorphous, polycrystalline, epitaxy materials, amorphous, polycrystalline, epitaxial, and flat surface, very low roughness to do heterostructures, control and thickness at the angstrom scale, avoid interdiffusion, that is sharp interfaces, that is moderate temperature. So properties includes the perpendicular anisotropy, magnetic coupling, size effect, critical temperature, domain wall and domain structures, and electrical properties from 2D material metals to insulating materials or semiconductors, right? So in heterostructures, we have different structures like GMR, TMR, SOT. So GMR represents the giant magnetoresistance, TMR represents torsional magnetic resistance, and SOT and DMI alloys or DMI that may heterostructures. The control of interfaces or surface properties. So various crystallographic phases and matter of 2D materials like graphene and titanium are being studied. Right? So these are the properties where we need to understand how the materials can be elaborated. So when we study about the properties are perpendicular anisotropy, magnetic coupling, size effect, where we have the critical temperature, domain wall and domain structure, and electrical properties from metal to insulating materials or semiconductors, and heterostructures like GMR and GMI devices, and TMR, torsional magnetic resistance, and or alloys, which is a combination of different materials, right? And control of interfaces on surface properties, and various crystallographic phases and state of matter, that is 2D materials of graphene and titanium. So in all this, we need to understand what is the basic fabrication method. So what is the basic fabrication method? Is a physical vapor deposition. The principle involved in physical vapor deposition is the evaporation, sputtering or sublimation of target under vacuum or partial pressure. Evaporation, sputtering or sublimation of target under vacuum or partial pressure. The vapor of atoms is transferred. The vapor of atoms is transferred from the source to the substrate under vacuum or controlled atmosphere and will condensate on the substrate. There will be a combination of adsorption, diffusion, nucleation, and deposition and desorption mechanisms. Right? There will be a combination of all these parameters like adsorption, diffusion, nucleation, and desorption mechanisms. So our substrate or underlayer will be of great importance for the growth. Right? So either what type of substrate we are going to use plays an important role for the growth of thin film, right? For the growth of thin film, right? Because some adhesive forces, because it had to stick onto that particular surface, it had to stick onto that particular substrate. The metal has to deposit, had to be absorbed on that particular. After it absorbs on the surface, then it nucleates, right? It nucleates. And your substrate or underlayer will be of great importance for the growth. Wedding, adhesion, epitaxy, crystallographic grade, all these are to be maintained, right? So the principle of physical vapor deposition, evaporation, sputtering, or sublimation of a target under vacuum or partial pressure. So the vapor of atoms is transferred from the source to the substrate under vacuum or controlled atmosphere and will condensate of the substrate, right? So this is how the physical vapor deposition takes place, right? So this is what your electron beam source, and this is your target, right? Electrons will try to absorb, right? So this is what some plasma is generated in case of sputtering. So that is what Ekin evaporation, right? So evaporation techniques includes the E-gun, that is what electronic gun. E-gun electrode deposition takes place, right? So those materials are to be taken in a crucible, right? In a crucible, and then they are heated, water cooled, and the electron source and water cooled, and the vapors are allowed to fall on the substrate, right? So this is what the Joule heating method, and this is what the Bunsen cells. So these are some of the evaporation techniques, right? So E-beam evaporation. Generally, E-beam evaporation, people use people take some material in the crucible and then subject it to some temperature through electron beam, electron source, and then it is cooled and the vapors will be absorbed onto the substrate. So this is what the evaporation technique, right? So what is the material evaporation? Typical evaporation occurs above 1000 degrees centigrade for metal, but for some species it starts from 200 degrees centigrade. Bunsen cells from 1000 to 1200 centigrade, and electron gun up to 4000 degrees centigrade. Melt the raw material source and evaporate it. Evaporation under vacuum 10 to 5 Pascal at least, and below 10 to 8 Pascals in ultra high vacuum systems. Avoid contamination. Mean free path larger than the crucible or sample distance, which is very much greater than directional flux. Directional flux good for liftoff, right? So it works for quite a lot of materials from metal to semiconductors, right? Some organics, that is refractive material as and refractive materials could be quite simple system to operate. That is what these are all to be maintained at clean rooms, right? Or very complex cluster of various chambers, transfer tube of 20 meter in Burberts, right? So these are some of the material techniques we need. So here there is no control of grain structure, there is no control of grain size or grain structure. Only the epitaxy, except the epitaxy, only epitaxy can be controlled, not for larger surfaces, not for conformal coatings. So heat to promote diffusion or ordering limited by interdiffusion between layers, and can be very important for metals. Example, nickel and manganese intermix at room temperature, right? So this is what the material evaporation, right? So heat to promote diffusion or ordering limited by interdiffusion between layers can be very important for metals. Example, nickel and manganese intermix at room temperature, right? So what is the PVD technology is based on vacuum techniques. So what are the physical vapor deposition technology? PVD techniques. PVD technology is based on vacuum techniques, right? Some conversion units, in SI units, we have the Pascal. 1 Pascal equals to 1 Newton meter square. 1 Pascal is equals to 0.01 millibar. 1 torr equals to 1.33 millibar. And the pumping elements that we require in PVD process like sputtering and all, we require different types of pumpings like diffusion pump, rotary pumps, right? Rotary pumps, diffusion pumps, and we have different types of pumps like diffusion pump, rotary pump, where we can have some high vacuum, right? High vacuum. And rotary pump to pump out the normal atmospheric gases, and we have turbomolecular pump, cryogenic pumps, and ion pumps whose pressure varies from 1 Pascal to 10 power minus 5 Pascal and 10 power minus 6 Pascal, which is assumed to be high pressure, high vacuum, right? High vacuum, and 10 power minus 8 Pascals, and plus N2 cooled panels and titanium sublimators to Degas chambers, right? to Degas chamber. So these are the PVD technologies based on the vacuum techniques. That means we need to have different types of vacuum technology. Vacuum technology is required. Vacuum technology like rotary pumps and diffusion pumps, right? So to maintain the high pressure or high vacuum. Okay. So because all this deposition has to be taken at high vacuum itself, high vacuum. Okay, so to get the high vacuum, we need to evacuate. This evacuation can be done only by using rotary pump. So how the growth principles takes place? The temperature of evaporation or sublimation is material dependent. That is 1200 degrees centigrade for transition metals. That is what we have the nucleation mechanism, right? So you can see a figure. This is your substrate temperature. So this is your nuclear mechanism. We have the group of islands, and we have deposition, we have dissociation. So diffusion along the edge, absorption at the edge, and diffusion across an atomic step, surface diffusion. Right. So energy of desorption is 2 to 4 electron volt. Desorption time at 800 Kelvin. That is 10 power 12 seconds for 4 electron volt, 1 second for 2 electron volt. That is what in case of metals. So energy of diffusion ranges from 0.1 to 1 electron volt atom frequency of 1 by omega, which equals to 10 power minus 11 seconds for 0.1 electron volt and 10 power minus seconds for electron volt. Metals to semiconductors, that is what need to heat. Right? So this is how the growth of principles takes place. So growth principles taken from one of the website, depending on the competition between energy of surface, interface, and misfit of crystal structures. Right. So material structure. This is what the material A, this material A and material B. We have the substrate and we have certain materials being deposited. Right. So misfit of crystal parameters lead to several relaxation mechanisms, that is plastic deformation and dislocation pins. So this is what the image we need of iron platinum. Okay, taken one of the paper, right? The material from one of the paper and one of the website. So that is what CF Andrew and O Flipchart slides on ESM website. Okay. So there we have taken this information from that particular website, and we set and some of the samples how the thin film is grown, by PVD techniques. So when we speak about the molecular beam epitaxy, complex systems is usually inside to analysis. That is read STM Auger XPS, and the deposition rate is around 0.1 ampere per second. Vacuum is less than 10 power minus 9 pascals. Ion pump plus nitrogen trap oven around 1000 degrees centigrade. So basic research on materials because of multiple possibilities, right? Multiple possibilities like co-deposition in situ annealing controlled by read, and two deposit per day, surface preparation, analysis, and sample interaction. So this is what we can see the molecular beam epitaxy system at CEA at INAC. So introduction, preparation, evaporation, analysis, ion implantation, STM or IPM and sputtering chambers. So these are all where we can have all this type of system there. So this is one of the equipment what we speak about, the molecular beam epitaxy, right? Where we can go the thin films. So complex systems is usually in situ analysis, read STM Auger, right? So that is XPS. Deposition rate is around 0.1 ampere per second vacuum, which is less than 10 power minus 9 pascals. Ion pump, nitrogen trap over a warm 1000 degrees. Basic research on materials because of multiple possibilities. 1 to 2 deposit per day can be done using surface preparation analysis. Right. So how the sputtering deposition takes place? Sputtering deposition takes place by the transfer of momentum. Right? Momentum of higher energy particles, momentum of ions. So argon atoms are used to sputter a target made of almost any material, that is DC for conductive, AC for isolate. DC means direct current. There is a DC magnetron sputtering for conductive and AC for isolating. Plasma is created by an RF radio frequency electric field, eventually enhanced by triode setup, that is extra E source. Operate generally at argon pressure approximately 1 pascals and at room temperature 10 samples per day. The reacting process takes place between the oxygen and nitrogen gas. That means as soon as magnetron sputtering, a magnetic field is used to confine the plasma. So here if you see, we have a substrate here and we have the sputtering target. This sputtering target is being given certain energy, right? So the atoms scatter in different direction. So when we inlet some higher energy gas, sputtering gas like argon, the ions will interact with that particular electrons, and start start adhere on the substrate, right? So in this way, how the thin films will be formed. Okay, so the reactive sputtering process is around oxygen and nitrogen. So this is how the sputtering deposition takes place. So then the plasma is generated. Right? When plasma is generated, right? So all the due to the positive and negative, positive argon plus ions and electrons having negative, due to this some potential in the form of plasma is generated and adhere onto the substrate, and eventually a thin film, eventually a surface layer is framed at the substrate. Right. The sputtering rate of ion and beam etching systems at actual minimum different yield of sputtering of materials as for ion beam etching IBE. Right. More conformal deposition than operation. Sputter material has any angle from 90 plus 90 to minus 90 degrees from the normal to the target, and deposition rate is around 1 angstroms per second. Oxides by AC sputtering of the target or from the metal and subsequently oxidation repeated. Right. Grain size can be controlled to some extent by the gauge mixture and pressure, and large scale deposition around 300 millimeter wafers, and the control of layer thickness down to few or even submonolayer. Method of choice for MTJ preparation, or we can go for MBE. MB is a molecular beam epitaxy, firstly used for Al2O3 and magnesium oxide for nanoimprinting. So fabrication of MTJ, that means magnetic tunnel junctions and membranes by sputtering. You have different layers here. If you see that there is multi-layer, so multi-layers will be multi-layer has been fabricated on a substrate, right? On a substrate, and we have some magnetic tunnel junction with magnesium oxides. So this is where the clean room facility, where we have clean room and people doing some work here, and right, and we can see certain magnetic field, and we have certain delta R by R, that is what the magnetic resistance. If you see, then the magneto resistance GMR can be around 186%. The impedance, right? The AC resistance is around 186%, right? At a normal temperature. So blue line represents the normal temperature and red line represents the temperature per 209 Kelvin. Right? So the GMR devices where we can find like this, right? So for different, but in the reverse field between minus 200 to plus 200 oysters, right? So state of art is 600% at 300. And delta R by R, whose ratio is around 250. So going layer by layer, low thermal barriers and refractory layers, we have tunnel barriers, storage layers, splitting layer, and high thermal barriers where we can see the magnetic tunnel junction with magnesium oxides. So whereas in case of pulse layer deposition, laser pulses supplement the target, formation of plasma takes place, and condensation on the substrate, crystallization on appropriate substrates. So this is what we need to understand about the PLD technique. So PLD technique is also one of the important sputtering, also one of the fabrication technique for the framing of magnetic nanostructure or spintronic devices. So laser pulses supplement the target, formation of plasma and condensation of the substrate, crystallization on appropriate substrates. So whose dimension is around 50 nanometers, 50 micrometers. This is also taken on oxides of STO, lithium oxide, yttrium garnet, right? So whereas in case of chemical vapor deposition, many different types. There's low pressure metal oxide, plasma enhanced, and often used in industry. Silicon third to fourth group elements, low vacuum, and high deposition rates, very good quality. Species introduced in the chamber decompose or react on the substrate. And whereas in ALD, that is atomic layer deposition, high K materials, but also metal barriers. So this is what the AMEC metal oxide chemical vapor deposition technique, where we can find all these 100 class clean rooms. So electrode deposition into nanophosphorus media. Electrode deposition into nanophosphorus media, where we have pores, membrane, gold cathode, and this is what the nanowires of diameter smaller than 20 nanometer and 20 micrometer thick, right? So electrode deposition into, so where we have, here we can see the CVD process. Many different types. Low pressure metal oxide, plasma enhanced, and often used in industry. And low vacuum, high deposition rates, very good quality. Species infused in the chamber, decomposed at reactonic chamber. Whereas in ultimate layer deposition, high K materials but also metals barriers. So we have 100 class clean room here, and then we can grow thin films by using this deposition technique also. In electro deposition to nanophosphorus media, we have certain pores on the surface. You have certain pores, you have membrane, and this is what the cathode substrate, right? So this is what the cathode platinum. Here we have anode platinum, and this is what the variation we can see. The nanowires of diameter smaller than 20 nanometer and 20 micrometer long. So this is what the electro deposition into nanoporous media. So where we are taking the magnetization by taking magnetization, right, by using VSM or vibration sample magnetometer, or you can go for magneto-optical carapace for different materials like nickel. We have the nickel type A, nickel type type B, and nickel type C, and cobalt platinum for different cobalt nickel and cobalt argent. So this is what we taken from one of the paper journal in Physical Review B, this in 2002. So multi-layers of cobalt 9.0, 9.5 volts, or copper -1.2 concentration, pure deposition of copper and cobalt copper alloys. So that's all. That is what we can understand behind these particular techniques. So material elaboration and nanofabrication techniques for spintronics, and there is a reason why it is difficult.
Like, share and subscribe. Hit the bell icon for more updates.